Studies Section 8, Optimal Control Theory. Introduction. The optimal control theory is an advanced methodology to the classical approach to dynamic optimization called calculus of variations. This theory can undo any problem the calculus of variations was designed for and further manage some problems that the calculus of variation cannot, such as corner solution and constraints on the derivatives of the function sought. The basic aim of this theory is to find the optimal time path for a control variable, which can be denoted as y. In this calculus of variations, the variable with which we sought an optimal time path is known as a state variable, which we shall designate as x. In the calculus of variations, the variable with which we sought an optimal time path is known as a state variable, which we shall designate as x. The state variables often have equations of motion set equal to x. Thus, the goal of the theory of optimal control is to select a stream of values over time for the control variable that will optimize the functional subject to the constraint set on the state variable. The optimal control theory problems that involve continuous time, a finite time horizon, and fixed endpoint are generally written as maximize according to the equation below. In equation 8.1, j is the value of the function to be optimized, while function of t is the control variable because its value is selected to optimize. J, x function of t, is the state variable that changes over time according to the differential equation set equal to x in the constraint and whose value is indirectly determined by the control variable in the constraint, and t is the time. The solution to an optimal control problem demarcates the optimal dynamic time path for the control variable y function of t. Example: let's consider an economic that produces output y using capital K and a fixed amount of labor L. The production function of the economic is given as y is equal to y into bracket KL. Output can be used either for consumption C or investment I. If we ignore the problem of depreciation, then I is equal to the K over the T. This means that investment is the change in capital stock over time. Thus, we can also write investment as I equal to y minus C is equal to y into bracket K L bracket closed minus C is equal to the K over the T, which gives us a first order differential equation in the variable K. If the objective is to maximize some form of social utility over a fixed planning period, then the problem becomes maximize integral u bracket c dt upper limit t lower limit 0 subject to the k dt is equal to y into bracket k l minus c and k into bracket 0 is equal to k naught, kt is equal to kt, where k naught and kt are the initial value and terminal value of k, respectively. Note that in the above example, the terminal state is a fixed value and not left free. Here c serves as the control variable and k is the state variable. The problem is to choose the optimal control path C function of t such that its impact on output y and capital K and the repercussions therefrom upon C itself will together maximize the aggregate utility over the planning period. The maximum principle. This principle is attributed to L.S. Pontryagin and his associates and is often referred to as Pontryagins maximum principle. This is the first order necessary condition of the optimal control theory. The statement of the maximum principle involves an approach that is akin to the Lagrangian function and the Lagrangian multiplier variable. For the optimal control problems, these are known as Hamiltonian function and co-state variable. The dynamic optimization of a function subject to a constraint on the state variable in optimal control involves a Hamiltonian function h similar to the Lagrangian function in concave programming. With respect to equation 62, the Hamiltonian is defined as shown below, where lambda function t is called the co-state variable. Similar to the Lagrangian multiplier, the co-state variable lambda function t estimates the marginal value or shadow price of the associated state variable x of t. In equation 8.2, the formation of the Hamiltonian is easy, and this is by taking the integrand under the integral sign and adds to it the product of the co-state variable lambda function t times the constraint. Let us assume that the Hamiltonian is differentiable in y and strictly concave so that there is an interior solution and not an endpoint solution. The necessary conditions for maximization are: 1. The h over the y is equal to 0. 2. A. The lambda over dt is equal to lambda is equal to the h over the x. B. The x dt is equal to x is equal to the h the lambda. 3a. X into bracket 0 is equal to x naught. B. X into bracket t is equal to xt. The first two conditions are known as the maximum principle, and the third is called the boundary condition. The two equations of motion in the second condition are generally referred to as the Hamiltonian system or the canonical system. To maximize, the objective function can simply be multiplied by -1 as in the concave programming, and if the solution does not involve an endpoint, the dh dy need not equal to 0 in the first condition. However, h must be maximized with respect to y. We shall generally assume interior solutions. Example: using the conditions in maximum principle, maximize integral 4x minus 5y squared in bracket dt, upper limit 3, lower limit 0, subject to x is equal to 8y, x into bracket 0 is equal to 2, x into bracket 3 is equal to 117.2. A. Set up the Hamiltonian. H is equal to 4x minus 5y squared plus lambda into bracket 8y. B. Assume an interior solution by applying the maximum principle. The h dy is equal to 0. 1. The h dy is equal to minus 10y plus 8 lambda is equal to 0. Equation 8.3. Y is equal to 0.8 lambda. 2a. Lambda is equal to minus the h over the x. Equation 8.4. Lambda is equal to minus 4. X is equal to the h over the lambda. B. S is equal to minus 8y. From equation 8.3, y is equal to 0.8 lambda. Then x is equal to 8 into bracket 0.8 lambda is equal to 6.4 lambda. Equation 8.5. Since we have employed the maximum principle, we are now left with two differential equations which we shall solve for their state variables x function of t and the co-state variable lambda function of t. Integrating equation 8.4 will give us the state variable lambda of t is equal to integral lambda dt is equal to integral minus 4 dt is equal to minus 4t plus c1. Equation 8.6. Substitute equation 8.6 and 8.5. X is equal to 6.4 into bracket minus 4t plus c1 is equal to minus 25.60 plus 6.4 c1. Integrating x of t is equal to integral minus 25.60 plus 6.4 c1 in bracket dt. S of t is equal to minus 12.8 t squared plus 6.4 c1t plus c2, equation 8.7. c. To solve for the constant of integration, we use the boundary conditions where x into bracket 0 is equal to 2, x into bracket 3 is equal to 117.2, and apply to equation 8.7. S into bracket 0 is equal to minus 12.8 into bracket 0 squared plus 6.4 c1 into bracket 0 plus c1 is equal to 2. c2 is equal to 2. X into bracket 3 is equal to minus 12.8 into bracket 3 squared plus 6.4 c1 into bracket 3 plus 2 is equal to 117.2. c2 is equal to 12. Thus, substituting c1 is equal to 12 and c2 is equal to 2 in equation 68 and 67. We have x of t is equal to 12.8 t squared plus 6.4 into bracket 12 t plus 2, equation 8.8. X of t is equal to 12.8 t squared plus 76.8 t plus 2, state variable. Lambda into t is equal to minus 4t plus 12, co-state variable. D. The solution for the control variable y function of t can be derived in two ways. 1. In equation 8.3, y function of t is equal to 0.8 lambda. So, y function of t is equal to 0.8 into bracket minus 4t plus 12 is equal to minus 3.2 plus 9.6 control variable. 2. Or take the derivative of equation 8.8. X is equal to minus 25.6 plus 76.8. Then substitute for x in the equation of motion in the constraint. X is equal to 8y minus 25.6t plus 76.8 is equal to 8y. Y function of t is equal to minus 3.2t plus 9.6 control variable. Evaluate at the endpoint. We have y into bracket 0 is equal to minus 3.2 into bracket 0 plus 9.6 is equal to 9.6. Y into bracket 3 is equal to minus 3.2 into bracket 3 plus 9.6 is equal to 0. Therefore, the optimal part of the control variable is linear starting at 0.96 and ending at 3, 0 with a slope of minus 3.2. Sufficient conditions. Assuming that the necessary condition, which is the maximum principle for maximization in optimal control, is satisfied, then the sufficient conditions will be fulfilled if 1. Both the objective functional f x of t, y function of t, t, and the constraint g x function of t, y function of t, t are differentiable and jointly concave in x and y, and 2. Lambda into t greater or equal to 0 if the constraint is non-linear in x or y. If the constraint is linear, the lambda may assume any sign. Linear functions are always both concave and convex, but neither strictly concave nor strictly convex. However, an easy test for joint concavity is the simple discriminant test for nonlinear functions. The discriminant of the second order derivatives of a function d is equal to fxx, fxy, fyx, fyy will be strictly concave if the discriminant is negative definite. Modulo d1 is equal to fxx less than 0 and modulo d2 is equal to modulo d greater than 0 and simply concave if the discriminant is negative semi-definite. modulo D1 is equal to fxx less or equal to 0, and modulo D2 is equal to modulo D greater or equal to 0. A negative definite discriminant indicates a global maximum and is therefore always sufficient for a maximum. An indicative of a local maximum is the negative semi-definite, which is sufficient for a maximum if the test is conducted for every possible ordering of the variables with similar results. Example: the sufficient conditions for the problem in the example under the maximum principle are given below. Let us start with the objective functional that is non-linear. We take the second derivatives and apply the discriminant test. D is equal to fxx, fxy, fyx, fyy is equal to 0, 0, 0, minus 10, where modulo D1 is equal to 0 and D2 is equal to modulo D is equal to 0. Thus, since both discriminant tests are negative semi-definite, then objective functional f is jointly concave in x and y. Given that the constraint is linear, it is also jointly concave and does not need testing. Therefore, we conclude that the functional is indeed maximized. This is the end of Echo 314. Thanks for listening.